My name is Pavan Singh. I work for Wind River. I focus on market and business development for industrial solutions. So Wind River, we've been around for 35 years. I won't go into a lot of detail, but we have the pleasure to work with most of the big industrial customers and companies across the world. And we have been a leading market share for real-time operating systems. And now we are really kind of moved into looking at entire systems, industrial systems, medical systems, auto systems, as well as aerospace and defense systems. So, when we look at the Industry 4.0, I think we have seen this term thrown around quite a bit. The main thing about the Industry 4.0 is, look, automation in the industrial world has been around for a while. Now, the cusp we are at is how do you bring the cyber physical systems to the industrial world? And that kind of a little bit of collaboration, a little bit of clash is what's causing the next generation of thinking. It is also the next generation of transformation for the industrial industry. The thing we want to talk about today is, from an architectural perspective, what is it that's needed to really make this Industry 4.0 a reality? And what's really blocking us? So if you think about that piece, what we are seeing till now, so we've all been in this journey of the industrial transformation in this space for about 5 to 6 years now. What we're seeing is that now that investment in IoT, it's starting from not just looking at initiatives and kind of high-level discussions to actually investing in real business value, business outcomes, and that's ending up into a lot of data-focused discussion. So people are saying, look, I've got data, what do we do with it? Because the industrial world has had data for a long time. To some of the IT world, data might be new, but not to this world. The problem in the industrial world was it was locked into proprietary systems. And now suddenly it's unlocked and now we can do a lot with it. Second part is, we talked a lot about cost reduction. The industrial world has been a lot focused on you build a system once and you don't touch it for 20 years. The problem with that is, over the span of 20 years, your maintenance costs go up. So where we're going is that cost reduction is now being seen as a need for more software defined. Rather than fixed, rigid systems, you're looking at software defined, flexible systems that can kind of be updated, upgraded, maintained over the course of those 20 years. And then security it's not just security from a checkmark perspective, but security from the build, from the get-go. When we think about systems now, we are thinking about connecting them to some sort of infrastructure. It might be a private cloud, it might be a public cloud. End of the day, that the connection is going to go beyond the facility. And that means that you think about what kinds of attacks can a hacker perpetrate, and how do you defend against? And the question is not whether there'll be an attack or not, the question is when. And the way I think about that is how do you think about, in case of cyber attack, how do you prepare before an attack? What do you do during an attack to minimize the impact of that? And what do you do once the attack has happened to make sure that you can figure out what happened and undo it? So that's a really big focus. And finally, is the automatic to autonomous. So how many of you were in the keynote today with the Boston Dynamics robots, right? You saw that this guy came on stage. He had this really smart robot, but he still had the remote control, right? So we are in that cusp where automatic very much was you design a robot, you move 3 centimeters here, 3 centimeters there with tight tolerances. That was kind of automation. Where we are going next is these automatic devices now need a lot simpler instructions, and they can do most of the tasks themselves. So you don't have to tell the person driving the robot on the stage straight didn't have to tell them lift the right leg or lift the left leg or look at the staircase. The robot was doing a lot himself or herself. So there's a shift from automation to autonomous. What that means is a lot more of the intelligence is fitting within the machine, and it's not left for the programmer or the coder to actually hard code. So now what that means is, if you step back, what does that mean from an architectural perspective? So if we step back a little bit, how did we land here? We started a while back with mainframes. You had these big computers, and people came in and time shared the resources. Then you went to a client-server model where you had decently powered clients and you had a lot more compute power on a server, and you kind of had this interaction. So we went in this kind of distributed client-server model. Then the last decade or so the internet has been focused on the consumer side of things. So we went to mobile devices and cloud. Cloud for a lot of the heavy lifting, infinite scale, mobile devices for a lot of power and connectivity right in your hand, right? But with the IoT, what's happening now is that we've gone from having one type of cell phone, right? If you think about our devices today, are 5 kinds of cell phones, and that's all we got. But in the industrial IoT world, you've got devices that are 20-year-old, you've got devices that are 5 months old, and you've got different form factors. So the range and the power of the devices varies a lot. So now, when you think about compute and the capabilities, we are talking about taking a view of what's available and being able to fully leverage it. To what that looks like is, you've got the cloud, you've got the fog, which could be an on-prem capability. You've got the device, which can be as powerful as a full-fledged robot, or as a small sensor, or you could have devices, again, could be a tiny sensor. So now the problem that we have to solve from an architecture perspective is, how do you optimize the resources to run across this continuum? And it's not just you design your continuum once. The continuum has to be designed initially, but then it has to be updatable and upgradable as time goes on. Because we know that our machine learning capabilities will improve, will change. So then how do you keep up with it? It's not designed once and then forget. It's designed once and keep on updating. So we go back to kind of the Kanban principles that we thought about, except that in this case, you're talking about the infrastructure itself. So if we think about what's really driving it, it's really kind of going from automatic to automated, which is, we went from automatic, which was you've got a controller hardwired to an I/O. It's supposed to do something and turn on a device, and then based on the control given to it. And then we went to automated, where we said, look, now I want to make sure that a robot kind of picks a device, places somewhere else, and then reads a barcode. That we call that automated. But the autonomous is where now you're not just not controlling it, you're actually now expecting it to be smart and react in real time to changing scenarios. And this is not just in a research project, this is actually happening today. If you look at the paint robotics today, some of our customers have their automotive paint robots looking at the paint that's coming out of the robot and looking at what the output is. If they notice a flake on the paint in a car, they redo the chemical composition of the paint itself. So it's a lot of smartness that's built in, because what's the cost? The cost is that if you don't change the composition of the paint in real time, the entire car might have to be scrapped. So there's a huge penalty, financial penalty to it. So that's the change in architecture that's causing it. If you think about what is architecture today, this is maybe a little dated. If you think about a few years back, we had, you know what, IoT is all about connecting today's architecture to the cloud. We said, you know what, get a connection, if you secure it, everything happens in the cloud and all the problems are solved. The reality was that there was this very rigid kind of a control HMI at the function, which are very kind of hard-coded devices. You had appliances which are kind of a server per application, and then you were kind of doing public cloud. The problem was that these were still hardware-based. They were still limited configuration. You couldn't really redeploy things. You couldn't really solve for bandwidth. And you couldn't afford to take all the data from this system here, send it all the way to the cloud, because guess what? The cloud providers charge you for the amount of data sent. So that wasn't really practical. So what has happened is we have two industries that we have used to learn this. One is the avionics industry. In the avionics industry, if you think about a plane, they used to have different servers dedicated to different functions of avionics. For those of you who haven't heard of avionics, is the functions that keeps the plane in the air. So each of these functions had a separate server, and now that would take space, power, and just the size of that, the weight of that was too much. So what we have helped the A&D industry do is take multiple of these systems and put them on one server, but make sure the avionics functions still function at that level of reliability, that the plane still stays in the air. That was one. The second part is in the telecom industry, we really moved from now these hard boxes that are slow-moving architectures to very dynamic architectures that can respond to 3G, 4G, 5G. So for that, there's been a move to the NFV kind of architectures. So these two industries we've helped them successfully transform from this rigid hardware-driven architectures to now more software-driven flexible architectures. And if you summarize all of that in one way, is that in case of avionics, if you think about it was different servers in a plane, east-west, kind of being consolidated onto one server. In case of telecom, it was kind of over the virtualization layer, over the different points of presence, over the different POPs, kind of virtualizing them. So we call that north-west. It's really virtualization, but it's very different from how do you think about that. Now in the industrial sector, we are really bringing them together. The east-west virtualization, which is in one location, different servers moving together, and then the virtualization across different layers in the stack. And what is happening is that the Industry 4.0 is also bringing the standard. This is a diagram from Industry 4.0, the German organization that's been driving this Industry 4.0 discussion. What you notice is they have taken the different layers, they've taken the different aspects of the solution, the field device, control device, to all the way to the world, and then created a set of framework that different players can come together and work together to build this architecture. Because guess what? The reason the architecture was so rigid was because one vendor would do the entire thing in one facility. They had no incentive to actually make it open, so another vendor could come in and talk to their systems. So as a result of that, you got proprietary protocols, you got hardwired communication, though that it went from one controller to a MES system, and that's all you could do. And if you had a new AI ML algorithm that wanted to use the device, you don't have access to the data, even though data is all there. So that's being solved. Second, from a standard perspective, is that cybersecurity is also being taken as more of a standards-based discussion, where NIST is looking at this entire thing, where they said, look, we can't just look at cybersecurity either from protecting one device to now, or thinking about tying the TPM, tying the OS down to a hardware. It has to be the entire life cycle. So you have to be able to identify what are the risks to both the people, the assets, the data, and the capabilities, from the assets, the hardware, the software, to the data, and then the risks to the people. And then how do you protect them? How do you detect what's happening? And at the end of the day, how do you respond to it? And the response is really, how do you respond during an attack and after an attack? And then how do you recover after that? So once an attack has happened, how do you bring back the system? And this is where the industrial world is very different from the IT world. If you think about in an IT world, if there's an attack, what do? You shut everything down. You said nobody can access anything at all. Whereas in the industrial world, you can't do it, because the number one thing you got to do is you got to make sure that the system is up and doesn't hurt other people. And the second thing, you have to make sure that system's up and running, because guess what? For an auto plant, if you shut down one factory for 1 minute, which is one car, they lose about $30,000. Now that is about into 40 is quite a bit of money. And if you think about a couple of hours, it's a couple of $1 million. So in case of industrial world, compared to the IT world, it's all about safety, second, availability, the system keeps on. And that's why the NIST framework is also being adopted. So what we're talking about is you have this architectural shift, and the standards are also coming together to really adapt it. So what does this mean? What does workload consolidation mean? What does software-defined architecture mean? Very simply put, it's taking some of these functions which used to be dedicated devices sold as products, and now really making a platform first that can actually be all of these or one of these, but then you don't have to redo or redevelop platforms for each of these functions. So if you think about what does a product mean? So if you think about whether you're developing a product for the industrial market or your customers are, in the past you developed one product. It was hardware, OS, software applications, right? That's all you did. You deployed once, you didn't want to touch it. In the future, if you think about a product, it's not just the hardware, OS, application, it's that included with the update services, security services, the microservices, and then in addition to that, you've got you want a capability to add additional content to it. So the product now looks very different. So the definition of product itself is changing in the industrial world. And so whether we talk to engineers who build a product, if you think about product management function itself is a very different mindset now as compared to what it used to be. What is the benefit of that? The benefit of that is you can now replace applications. You might have a control function running here. So think about that. This is a embedded virtualization. So you're talking about virtualization that doesn't impact your performance, your control function performance, while still allows you to get the performance of a control function, along with now the capability to run a Linux and for example, a comms capability on top of it, and you might want to run HMI on it. In the past, the mindset was, we cannot do that because I don't want to compromise the functionality of the control function. But with some of our investments, a new platform we will launch early next year, now you can actually do that. You can actually have that joint product. And so in addition to that, in the future, when we talked about being able to update content, you've seen demos where a robot is using machine vision to figure out what's going on, whether it's barcode reading or whether looking at paint. But really what you want to be able to do is right next to this control that's sitting next to a machine or a robot, you want to add new machine vision or AI algorithms. But it's not just that, because the AI algorithms are updating as well. So today you might have an algorithm, but tomorrow you might have a better one. So you want to be able to change it so that your performance improves. So you want to be able to add additional content. What happens is with this kind of virtualization, when you add new content, you don't have to rebuild your entire product. And your control function, which was certified to some or tested extensively, doesn't have to be retested. And if you've got some sort of safety function, that doesn't have to be recertified. So what it does, it gives you that capability now to have that reliability of an industrial product, but with the additional now capability of being able to upgrade, maintain, fix it on the go. So the one more thing that, actually going back to this thing, one more reason a lot of our customers are using this capability is they're now building one platform that goes across multiple product lines. So that just means that instead of multiple engineering teams developing separate products, they have one platform, and on that you can run multiple functions. So that's more of an engineering cost saving. And then if you think about safety, how many of you, by the way, deal with safety in your product development, or have you heard of safety? So safety is very simply put, is the way that machines shouldn't hurt the world. If you think about that, now what you can do is, with this level of virtualization where we have implemented robust time and space partitioning, so one workload doesn't affect another. Now if you've got now you can actually have a safety island that's kind of the control function and make sure that it meets the safety requirements that is needed for your application. But now within that, you're also running your other comms non-safety intensive products or workloads right next to it. And you're now making sure that if you do need to update your safety workload, you just have to retest just that thing, not the entire platform. So if you know in safety, testing is a very expensive task. So by being able to separate these workloads, you can even have multiple safety islands, and then you can actually have safety security implemented separately alongside each other and look at testing and building each one of them separately. So now you can have on these products satisfy the requirements of safety and security all in one go. We call it the safety and security islands. Part of that is, if you think about islands, they are connected, but they don't affect each other as much. There's a sort of separation between the two, so you can meet your requirements. And then you might even have a set where you have multiple safety islands, and then you have a security island right next to it. So if we think about the capability of this product, the initial product, a controller, now has gone from running just one control function to being able to run multiple control functions, and running a security workload, running a comms workload, and AI and ML. So that's the vision that we are going after. So if you think about what we're doing is we have an offering that meets this requirement, which is an embedded virtualization that meets the stringent requirements of industrial world. We've got OS that meets the real-time requirements. WindRiver's got a Linux distribution that meets all the long-term support requirements and really helping you build this system. And you might want to start with just this layer and the control function and then build others later on because you have that flexibility now. In the past, you didn't. So why now? I think the reason that we're excited about this now is, number one, we are moving from single core to multi-core. There were multi-core chips being used in the past, but a lot of the customers kind of shut down most of the cores and use a multi-core chip as a single core. But now with the kind of partitioning we're talking about, kind of virtualization we're talking about, now we can actually use these cores. So it makes sense to use something like an A53 or A72. Second, you're looking at size, weight, and power. There is robust isolation available. So now you can actually run those multiple safety workloads, security workloads, right next to something, to a graphics workload. And then you also want to make sure that when you develop a platform, you develop an IP, that you don't have to redevelop that for a different hardware platform. So in some ways, we are trying to abstract away from tying your capability of the product to the hardware platform. You want to reduce the cost to kind of translate the IP that you got today into a new hardware platform. Because in some ways, as the hardware capability of the embedded platforms improves, the velocity of innovation is also improving. And in some ways, we have to keep up with it. So we talked a little bit about this architecture. So we said, like, look, it's rigid today. You've got separate functions. You've got separate servers. And you can't really do a lot. We thought public cloud connection will solve everything. It didn't. So the architecture we think will evolve to is you will have kind of multi-function products. Instead of dedicated functions for HMI or control, now you have a product that can do multiple things, right? And it's flexible. And then at the server level, you've got virtualization that can now have multiple functions, even a historian or a control function at that level. And then the cloud can play a lot of these functions, but then it plays more of a supervisory role. So if we think about the parent-child kind of analogy, here is where all the fun happens, right, in the factory or refinery. And the cloud becomes more of a supervisory role where when it comes to security updates, when it comes to really making sure that you've got some of the business services, you've got some heavy analytics workloads where you're creating the feature models. So that's what happens in the cloud. If you think about AI, the feature extraction of a model might happen in the public cloud with infinite scale, but the actual implementation of the model will happen right next to an industrial machine or a robot right down there at the control level. So because you've got the capability now to either deploy models, but also update them on the fly as you need it. So we think that this architecture is really going to help enable the industrial world into this next generation of digital transformation where you're looking at adapting to reducing costs, deploying new security capabilities, really moving from automated to autonomous as a trend that we're talking about. So how do we look at it? So for us, we look at this architecture in terms of the OT edge. We focus on the OT edge. We're not a public cloud provider. So that edge is the operation technology edge. We look at two parts, which is the far edge and the near edge. Far edge was the one we talked about, device, the sensor, the robot. And then the far edge is kind of almost the on-prem cloud server. So we think about that. Far edge, we have got the real-time, the Linux, the hypervisor. So it meets all the requirements for that level. At the near edge, you're looking at more of you still got those capabilities, but you're looking at scale, at the IT scale. And this is more of an on-prem cloud side where you might run computer vision, you might run AI, but this is more the heavier workload, more a feature extraction than running a model. So now that combined with the orchestration, security, and lifecycle management capabilities, we think that's the architecture for the OT edge that we just talked about, but it really becomes the underlying infrastructure that really gives the flexibility to meet your demands today, but then also keep up with the market. So in summary, so the business, if you look at the business benefits, there are four of them. Number one is that, hey, we reduce our BOM. We combine multiple systems into one. We reduce the complexity of a single device because you can now, if you've got a device that is software driven, now you can update and maintain that so much easier. Now the device itself is modular and portable, so you can fix if something breaks. It doesn't bring the whole factory down. You can fix one partition, one of the virtualization layer at one time. We can reduce space and size, so your OpEx gets reduced. Now for safety and security can be implemented effectively. And lastly, it really enables innovation. So what happens is that with this kind of architecture, we call this workload consolidation. And in some way the term is it means something, it means a different people. But hopefully we have given you a sense of why it's something to think about and why virtualization, both at the controller level and the server level, are really important to think as not as separate things, but in tandem. And in some ways, we have products that address both, and we also have bring this together as a system. So lastly, there's a demo at the Wind River booth that kind of demonstrates that. The platform here, right there, that runs on ARM A53, is the platform we will be officially releasing in February, but we're demonstrating it now. It shows the VxWorks real-time OS running OpenCV. It looks at a Wind River logo and real-time tells you that it detected this. It communicates that with more of a non-real-time workload with a web server that changes the image that pops up. And so it shows the response that, look, you're running a real-time workload, you're running a web-type workload, all on that one device. So make sure you stop by there. With that, thank you very much for listening to me. And if you have any questions, I would love to talk to you and understand whether this direction was something you see as important or not. Thank you so much.